further, without any equal sharing, you may end up with transfer electron to the other atom altogether. Okay, so one atom would exert in a polar bounded molecule. One atom exerts a greater attraction to the electron, resulting in a more negatively charged atom or ion. If we don't want to use the term ion there because they are not ionic. Okay, so in this case, what happens there? Why do one exhibit a stronger attraction to the electron than the other? Well, the thing here is that when we try to determine the polar bound there, a covalent bound in terms of their polar nonpolar nature, we can actually look at the actual values of electron activity for the two atoms involved in it. Now, if the difference in the electron activity between two atoms equals to 0, like hydrogen to hydrogen, 2.1 minus 2.10, fluorine to fluorine, 4.0 minus 4.0, 0. Okay, so if the difference is 0, we say the chemical bond is pure covalent, equal sharing. Now, that only happens when you have two same kind of atoms connected with one another. However, sometimes when you have two different atoms connected with one another, the difference may not be as significant. It's probably a little bit more than pure covalent, and the difference is greater than 0, but it's not as significant without being able to without the possibility of resulting in a obvious separation of charges there. So if the difference is between, say, greater than 0, between 0.1 and 0.4, we would say this is a non-polar covalent bond. So we are talking about two extreme situations within the covalent bounding. Okay. One is a pure covalent, the other is polar. Now in between we have non-polar covalent. And then if the difference is between 0.5 and 1.9, greater than 0.4 but less than 2, then the covalent bound is said to be polar. Now if the difference is equal or greater than 2, you end up with ionic. So you see a transition going from equal sharing in between the two atoms for the electrons and to electron transfer. And we can actually quantify whether a bound is polar or non-polar or even ionic based on the differences of the electron activity between the two atoms involved in a compound. I wouldn't even use the word molecule simply because we could also judge whether or not a particular compound is ionic. If the difference is 2.0 or larger, then we have an ionic compound. Okay? So in this case, how do we understand the separation of charges there? Now, if you have two same atoms bound together, they have equal ability to give or take electrons between one another. Well, the difference between the two is 0. Now, if you have, say, oxygen and fluorine, okay, the difference isn't really that big, resulting in a closer to equally shared electrons there. So within a certain range there, as long as the difference is less than 0.4, well, we would say we have either a pure or non-polar covalent bound. Pure covalent bound is the difference when the difference equals to 0, and non-polar covalent bound is when the difference is less than 0.4. Okay, so if we have something that the difference is greater than 0.4 but less than 2, then we have non-polar. We have a polar covalent bound there. And then if the difference is equal or greater than 2, then say, well, electron has been transferred. Okay, so how do we determine whether, in terms of the bound polarity? Well, all we need to do is to have a table of the electron activity. Now, I know I asked you to memorize a lot of things there, and that table is not something that I won't ask you to memorize. So we will give that table to you. If we ever need you to judge the polar nature of the bound polarity there, we will give you the values for the elements, for the electron activity for different elements there. All you need to do is to remember the range between 0 and 0.4, non-polar, 0.4 to 2, polar, and greater than 2, ionic. Okay, so this is when we try to determine whether a particular bound is polar or non-polar, we also use the term to describe the atomic molecule. Okay, now diatomic molecule, polar or non-polar, it solely depends on whether you have a polar bound. If you have a polar bound in diatomic molecule, the diatomic molecule meaning you only have two atoms connect with one another. Okay, and if you have a diatomic molecule and there is a polar bound in there, then the bound is, well, if the difference between the two atoms there, in terms of their electronegatividity, En stands for electronegatividity. If the difference is equal or less than 0.4, then we say the bound is nonpolar, molecule is nonpolar. Okay. Now, if the difference is within this range, equal greater than 0.5, or less than 2, we say the bound is polar, the molecule is polar. If the difference is equal or greater than 2, we say the bound is ionic, the compound is ionic. Okay. So this is how we determine the polarity for a diatomic molecule. For diatomic molecule, if you have polar bound, you have a polar molecule. Okay? So that's something that we do want this particular range from 0 to 0.4 to 2. This is something that I need you to memorize. Okay? That range. How do we determine whether a bound is nonpolar on that range? Difference less than 0.4, equal or less than 0.4, that's the nonpolar. Between 0.5 and 2, less than 2, that's polar. Equal or greater than 2, and that's ionic. Okay? So this is something that we need you to remember, and we need you to be able to use this information. Given a table of electronegatividity, we need you to be able to judge whether a particular chemical bound is polar, nonpolar, or ionic. Okay? And talking about, and giving you some examples there, talking about, say, hydrogen is supposed to be 2.1 there, 2.2, put it in there. So hydrogen and fluorine there. If you look at the bound between hydrogen and fluorine, 2.2, 4.0 difference, or even 2.1, 4.0. Difference is 1.9, 1.8. That's greater than 0.5, less than 2. So this is a polar covalent bound. One would say this is an extremely polar covalent bound because the difference is very close to almost ionic, but it's not quite there yet. So we can also calculate, based on the difference between the two atoms in a particular molecule there, we can judge whether a particular chemical bound between, among different types of covalent bonds there, which one has a higher polarity. So using fluorine as our reference point, and we look at the hydrogen and carbon and oxygen. When hydrogen combines with fluorine, when oxygen combines with fluorine, when carbon combines with fluorine, you each form a covalent bound. And when you take the difference in terms of the electronegatividity between hydrogen fluorine, carbon fluorine, and oxygen fluorine, you can see a hydrogen fluorine 1.8. That's the difference there. And carbon fluorine 1.5. Now 1.8 is a bigger difference than 1.5. So we would say the bound nature, the polarity of the hydrogen fluorine bound is stronger than carbon and fluorine. And if you look at the oxygen fluorine 0.5, well, oxygen fluorine 0.5 equal or greater than 0.5 is a polar bound. So this is a weaker polar bound, the weakest polar bound among all three. This is the strongest polar bound, simply because of simply based on the difference of the electronegatividity. So using electronegatividity, we will be able to determine whether a bound is polar or non-polar. We will also be able to determine between two different types of chemical bound, which one is more polar. The higher the difference, the higher the polarity. Okay, so it's a fairly simple comparison there. And as I told you, after the second exam there,